So no videos today, but why don't I do a live one? I guess I can't remember where most of these things are. This is Niagara Falls, I think. I don't know if you knew that Niagara Falls, they turn off the falls at night and they divert the water upstream around the falls. They don't go dry, both on the Canadian and American side, and they generate power for the 100-foot or so drop and the very large amount of water that drains. That's a dam being built in British Columbia, I think. That's Alberta. Hoover Dam, as it used to be before 9/11. Used to drive across the top to get from Nevada to Arizona. And then after 9/11, you remember the Dam Busters movie. They thought that it was a vulnerable structure, and so I think built a bridge across from one side to the other. That's not the bridge. I think that's also Hoover looking upstream. That's another dam on the Colorado River. Our house, unrelated. Don't know where that is. And I'm not sure. Might be Watertown, New York. Oh, Fenelon Falls, Ontario. And so I guess the other use of dams is to provide locks. The Trent Severn Waterway takes you from Lake Ontario to Lake Huron through Ontario. And there's a lock in there somewhere, but it looks like they're also producing power. There's an outlet here, and this looks like a low-head powerhouse somewhere in BC, Hoover Dam. Actually, with the new visitor center, this was probably 2003 when we took a bunch of students out west to look at energy, and this is a new bridge that doesn't go across the dam. Took students to Iceland. This is somewhere on the Reykjanes Peninsula in Iceland. Iceland, blessed with lots of water and lots of geothermal based on the fact they're on the mid-Atlantic ridge. But hydro is a big thing for them. And not without controversy. There was a big movement in Iceland that wanted to not go to renewables, specifically hydro, probably in the 1960s. But the interests of energy, I guess, prevailed. Tidal dam in the UK. Tide comes in, you capture it behind a barrage. Tide goes out, you let it flow through the barrage, and you do that with each tide every 6 hours. This is probably from the 1700s, and you use it to grind grain. I think that's Hoover Dam as well, the spillway. Hoover Dam from the top. Hoover Dam. Dam in the middle of Australia on the Snowy Mountains project. I don't know if it's tagged with location. You'll be lucky as engineers. You'll get to travel on someone else's dime. And when you finally get a real job and aren't paying for someone to talk to you, which will be a landmark, I'm sure, for you all. And so that's just the upstream of a dam. That's in Sonoma County, just outside, on the way to UC Davis. I remember we were going. Looks like Niagara Falls again. Don't know what that is. I couldn't work out where that is. Don't need to know. That's not a dam. That's Lisbon. We took students to New Zealand. We should take students to New Zealand every year. 2023 was the last one. Before that, we cancelled. I remembered that before we were about to go on the Tuesday, they cancelled all overseas trips at Penn State. We were going to go on the Friday. So this is spring break. So this is the Arapuni Dam on the Waikato River in New Zealand, North Island. And New Zealand is the North Island of New Zealand. So this actually is here. Taupo is a volcanic lake. There's a river that goes from Taupo all the way almost to Auckland. It's called the Waikato. And actually it's basically dammed every single piece of the way. And so Arapuni Dam is one of those many dams that takes the catchment that arrives, everything feeds into Lake Taupo and then goes downstream for that. And there's even a different watershed here that has a dam on it that they pump the water upstream to get it into Lake Taupo so they can use all the dams that are already installed, the big capital expenditure on that, without building new infrastructure by pumping upstream and then using the infrastructure on the dams as they go down. So that's Arapuni Dam. So the water comes from up here behind. This is the turbine house I don't think I've got any pictures of that because I just searched on dams, so it doesn't see that. So that's the upstream dam that diverts it into it. Actually, it's a bit damaged from earthquakes in New Zealand. Other dams in New Zealand. Not a dam. That's Wairaki geothermal field and condensers, cooling towers to be able to cool the water down and get the energy out of it. That's somewhere on South Island. Hoover Dam again. In the days before Photoshop, when you used to have to make photos by splicing them. Kyoto in Japan, as it turns out. That's also in Iceland as well. Burfell Dam. In May, I guess, a little cool, but no snow you see. And I guess that's an interpretive board on how the dams work and how they're linked and what they look like as they go down from location to location, ultimately to the sea. Landsverken is the company in Iceland. A drainage channel supplying water to a dam in basalt, cut in basalt. That's in the southern UK. That's in Spain. Dams which have lost their water in drought. The original bridge at the bottom, supplanted by an elevated bridge when the dam and lake were there, I guess. Shown, I guess the other day I saw that the Yucahany Reservoir at the top of the Yucahany was down at an all-time low, and the US 40, the national road bridge that had been submerged by the dam and left, was now not submerged anymore. That's on the way to Dulles Airport. That's in Scotland, just upstream of Fort William. So Fort William surprisingly has an aluminum industry. It's in the middle of nowhere, but the reason it has an aluminum industry because the big expensive input into making aluminum from bauxite is electricity. And so you need either geothermal or hydro power to be able to do that effectively. And so that's Scotland, just before a whiskey for lunch, as I recall, somewhere in New Jersey. I think the highest thin arch dam in the world now in China, Jinping Dam, not named for President Xi Jinping, but that's standing on the arch. I think it's a 300-meter tall arch. I don't know if it's linked to this. It's in western China, just at the edge of the Himalayas. Himalayas are the water tower of the world, supply the world with all the water. Brahmaputra and the Ganges go out through India. The Yellow River and the Yangtze go out through China. The Mekong goes out through Vietnam, I guess. All huge rivers draining the western Himalayas. Don't know if you can see it here. This dam is here. You can see the river goes up here around a big hairpin bend. And so this dam dams the water upstream, which is this side, has a tunnel that goes through the mountain to the lower elevation of the river on the other side. Must be lower, right, because the river's flowing downstream. And then uses this short path to be able to generate electricity. And the reason I was there, because it's also an underground research lab. So to do things like look for neutrinos, you have underground labs, which are, this one is 2,400 meters below the surface, and very low background radiation from cosmic particles. And so you can look very carefully at neutrinos as they pass through with big detectors in the subsurface. So you see all the what they call dental work on the downstream side of the dam. This is the dam. On the left side of this is water. Bungee jumpers in Australia. You can see the cord, but no one on the bungee jump. And this is Tasmania, Hobart. Not Hobart, but Tasmania. So-called, this is from a year ago. They want to be the battery of Australia. Right now, they sit in the roaring 40s, 40 degrees south latitude. No, it doesn't look like it's come up on the thing. And so right now they produce 100% of their own power by renewables, mainly hydro, some wind as well. They sit in the roaring 40s, so they get lots of water and lots of constant wind. And these are the tubes taking the water down from the upper dam to a pump house at the lower reaches where it's dispensed into the lower river. And their plan is to generate 2 times their needs by renewables. The Battery of Australia, and then across the Tasman Strait between Tasmania and the mainland Australia, Tasmanian Australia, transferred by DC power. And this is near Lake Champlain. It is a hydro plant, very rural. Can't remember. Does it say what it says? Oh, it's on the Au Sable River. Yeah, Au Sable River. So it's on the west side of Lake Champlain, Burlington, Vermont here. And so they just collect water upstream, and then they're putting it through a pump house and spilling some of it here, I guess. So that's it. So that's dams for you. And so it does relate, I think, to what we've been talking about. What we'll do today is talk about pipe networks. I guess it's the final part of our pipe quest. Maybe in terms of recap, it's useful just to say what we've done so far. This kind of summarizes it quite nicely. We talked about the methods by which we can solve for head losses in systems. And we talked about these type 1, 2, or 3 problems, and they are based on what you know about the system, and what you want to know. If you want to know what the head loss is, and you know flow rate and the dimensions, easiest one because you have a velocity, you can immediately calculate from the dimensions of the problem the Reynolds number, so you know what flow regime you are. Directly you can get friction factor, and therefore you know head loss just from this expression. One-stop shopping, and no iteration needed. If you want to be able to calculate velocity, it becomes a bit more challenging because you can't immediately calculate Reynolds number. So you have to select a friction factor. We know the rough ranges of friction factors are between 1/100th and a tenth and a 100th. Practically goes to 1,000th actually for some of them. But we have a range for these. We know that they're different for laminar or turbulent, so you could make an educated guess about that if you knew something about roughness. But if you don't, then you just have to choose a friction factor. You can calculate a velocity from this expression here. This expression rearranged is just this, square rooted on both sides, so you can get a velocity. If you can get a velocity, you can get a Reynolds number. If you get a Reynolds number, you can check the friction factor from our Moody chart. And so you're always on this. This is an Euler number, which is also equal to a friction factor. This is a Reynolds number. And we know we have these 2 regimes. One where the friction factor varies with Reynolds number. C is usually 64, and one where the friction factor is constant and varies with EO, relative roughness, epsilon over diameter, right? And so you can make an educated guess as to where you are. Once you have the Reynolds number, you know where you are in this regime, and you can figure out exactly what your new friction factor would be, and then go through the iteration however many times you need to do to be able to get the solution you want. So that's type 2, and type 3 is where you want to choose the dimensions. You know you want to get a flow rate of X liters a minute to your bathroom. You want to know what pipe size you should use to do that, and so you need to do the same process. You don't know the velocity. I guess in type 2 and type 3, you don't know the velocities. And so you want to be actually you do know the velocity in this case, because you have a flow rate. And so you want to calculate the dimensions. So you choose the dimensions. You've chosen a velocity at which you supply X liters a second to your toilet. And so you get a Reynolds number. Reynolds number gives you friction factor from this. Friction factor gives you, for a given head loss in our system. Head loss would be, in the UK, lots of people used to have a header tank in their attic. So the water would be pumped into that, and it would just rest there, and that would be the motive force through the system. In State College, you see some water towers placed in the system. Same idea. If you get water from a well, then typically you have an expansion tank which has a bladder in it, which is pressurized, so it provides constant pressure to the water that comes into your house. So you know the pressure that's being applied. You know everything else in this, so you can get the diameter. You choose a diameter. You calculate a diameter from this. You check it again to see if it's the same diameter you chose. If it's not, you calculate a new friction factor. New diameter gives you a new velocity because you know perhaps the flow rate, not the velocity, and you go through the system again multiple times. So that's what we did last time. So not so exciting, I don't think, in terms of pipe flow, but something probably bread and butter work for what people do in terms of calculating these things. So we have a couple of things left to talk about: pipe networks and pipe flow. And so pipe networks are where we have multiple networks, which we'll spend most of our time on that. I don't know whether to use our notes or whether to draw it out. I'm not sure what leaves the most lasting impression. It's written down here. But the idea is that we can have flows in either parallel or series. And whether we have flow in parallel or series defines how we deal with it. So what we'll do is we'll look at these simple geometries, a branching geometry, and then we'll do a couple of examples, and then we'll look at methods of being able to measure flow rates. So the idea, we know from what we've talked about, continuity requires that if we cut this either upstream or downstream, then V1A1 has to equal V2A2. And so those are also equal to Q, right, by definition. And so we know that when we go through this pipe network in series, the volumetric flow rates or mass flow rates, if we choose to multiply it through by density on both sides, have to be equivalent. And so that means that this is a requirement. But we know also that the head loss is going to be equal to friction factor length over diameter times V squared over 2G. And so if we think about that, and we think about what the head losses would be on section 1, head losses in here, as we go to section 4, then we know that the diameter is reducing as we go downstream, so that's getting smaller. And we know that the velocity, because the diameter is reducing, has to be increasing as we go downstream. And so as we go downstream, I'll just use an arrow to represent that. I'm good at pictorial representations. Since this increases and this decreases and it's in the denominator, then the head loss has to increase as we go downstream. And so we know that if we draw it, say, from upstream to downstream, I'm going to draw this. This is going to be my attempt to represent this system. It's probably worthwhile drawing this. If we don't have this. So we have an upstream head. We have a downstream head. And this would be delta Z. And we know we can either take a point here and here, or we can take a point here and here. We get exactly the same results because these are stagnant tanks, and this would just be a static head of water. So we know that if we look at our energy equation, we get something like Z1 minus Z2 plus P1 minus P2. I'm just moving the terms from the right-hand side over unit weight, plus V1 squared over 2G minus V2 squared all over 2G, plus HP equals HL. If there's no pump in the system, which there isn't in this particular case, then we ignore this. And so we can either write Bernoulli up here at the top, which is easiest, so it's just delta Z. Pressures are 0 at this place. Velocity, big tank expression, so everything drops out. If you want to write it upstream and downstream, actually it's not so convenient here, right, because the velocities don't match up as you go downstream, so let's not do that. So let's just write it at points 1 and 2. And if we do that, then head loss is equal to this. So we know that the head loss over this whole system has to equal this amount, and I didn't leave myself much space. So you could think about the head loss from going from upstream to downstream. This is just the x direction. This is the head. And the head loss will look like this, you'd expect, on a pipe that doesn't converge. But we know that it has to be these magnitudes. The total head loss has to sum to that. Bing. Right? We know that we go from upstream to downstream. It makes sense that they must sum to the same magnitude over the top. So we know that we sum them from place to place. The utility of doing this is that this shows that as we get a smaller pipe, the overall head loss must increase. And so if we were to look at what this might look like schematically as we went down from upstream to downstream, then we know that the head loss as we go downstream has to either look like, don't do a straight line, it has to either look concave downwards or concave upwards, right? Because it has to end up at this total amount as we go across it. And we know that we get less head loss upstream, and so we could rationalize that it's actually going to look like this. If these pipes were all individually the same length, then this is a small head loss between upstream and there, bigger head loss. So the head loss incrementally would be this amount here. This would be HL3, etc., and the others. So we can rationalize that. And so if we know what the flow rate is, we can calculate the individual components and calculate the head loss over the system. If we have a system that looks like this, here we've drawn the big tanks upstream and downstream. We know that this also is going to be the same head loss between, we can either draw a circuit through this going along here, or we can also draw a circuit through this and going up here. And we know Bernoulli through those would be the same things. So the head loss for circuit 1 and the head loss through circuit 2 have to be the same because it's exactly the same end conditions here. And so we know that the head losses through the system are identical for each of those flow systems, but we get Q1 coming out and Q2 coming out, so the total flow through the system is just going to be sum of Q. So those are the conditions for pipe networks. So that makes system sense as well, right? If we look at more complicated systems, then we can do exactly what we've done before. So it makes a difference whether it's in series or parallel. I suppose for many of these hydro systems, this would be exactly what those 4 or 5 pipes going downhill in Tasmania would be. They're parallel pipes. The head losses across the systems would be the same. And of course, within this system, we'd want to have turbines. We'd be able to match the upstream flow rate with the downstream, well, calculate the flow rate. And I guess the other interesting thing that we could do would be that if we go back to this expression here, and we write that delta Z plus HP equals HL. If we know that HP is equal to power, big W dot, rho G times volumetric flow rate. And so we can rewrite that as we have actually already, that let's assume that this is 0. No head losses in our system, just to make life easier. So HP equals delta Z, negative, I guess, if we want to be consistent. And so in other words, if we write that out, this would be equal to delta Z. So in other words, very straightforwardly, we get that the power from a dam is equal to the density times gravity times the volumetric flow rate times the head drop. Simple. No losses in the pipes. We want to have big diameter pipes because we know big diameter pipes have the smallest losses. Big diameters, smallest head loss. So that will guarantee that this goes to a small number. And so this is just equal to the mass flow rate and delta Z. So the mass flow rate is controlled by how much rain you get, and you don't make dams in the Netherlands to generate power because there's no elevation. You need elevation gain to do it. That's why Norway has so many, and that's why they want to become the battery of Europe. I guess I'm not sure they use that term, but that's essentially what they want to do from last time. And so that's a useful number. You can also calculate the maximum power out of a wind turbine as well, just by using these same things. Perhaps we'll do that next time when we talk about external flows. So, but I digress. So loop systems, so a bit more complicated. You can imagine that you can write Bernoulli exactly the way we did previously, and you could write it on a circuit that goes from A to B, but goes through pipe 1s and 2. And if you do that, then you'd end up with the upstream tank conditions here in A. You'd end up with the downstream tank conditions here in B, big tank assumption. And you'd end up with head losses in pipe 1 and pipe 2. So you'd end up with this equation if you take the top circuit that goes out through this. If you take the bottom circuit that starts off here, goes part of the same way, but then digresses to come here, then you end up with the, again, the upstream tank, the downstream tank, and the head losses on the first circuit and the second circuit. These obviously, since you end up with the same head at this point here, the drop between here and here has to be the same. Head is going to be the sum of pressure, elevation, and velocity at this point. They have to be the same at this exact point. And so this means that since these two expressions have to be the same, that these have to be equivalent to each other. So the head losses on this final section, if you were to draw them out, I'm not sure if I have enough space to do that. I guess you could draw this as the elevation Z up here, and you could draw this as the elevation Z here. You know that when you go through this system, then it has to look like this. This is the head loss in pipe 1, which would be, physically, it would be this amount here. And conveniently on that crease, the head loss in pipe 2 and in pipe 3 would be this. And it has to be this because they end up in the same tank. So you can use that to be able to solve it. And so for all of these systems, actually, if you look at the very big picture, to solve it, and we'll solve a couple of them, you can look at it that we have maybe 3 variables. We have V1, we have V2, and we have V3. And we know that these will turn up in these components here, right? Head loss is equal to friction factor, length over diameter times v squared over 2g. And so maybe we know the dimensions of these pipes, so we'd know L. Maybe we can guess the friction factors, but we probably might want to know what the velocities are. So if we don't know what those velocities are, we have three unknowns, and so we need three equations to be able to solve them. And so typically, in this problem, the equations to solve them will be that V1A1 equals V2A2 plus V3A3, right? This is just Q1 equals Q2 plus Q3. All right. What comes into this pipe and ends up at this point is split. Some of it goes here, some of it goes there. That's really what this is saying. So that's one equation. And we can write Bernoulli between upstream and downstream, and we would have something like HL 1,2 equals friction factor length over diameter 1 V1 squared over 2g plus friction factor 2 L2 D2 times V2 squared over 2g. And deliberately, these aren't nodes, these are the velocities in these conduits, these pipes. And then we have a head loss in 1, 3 in the other circuit, the lower circuit in blue here, which is going to be the same initial term, F1, L1, D1, V1 squared over 2g, plus a new term, which is F3, L3, D3, V3 squared over 2g. And so if we ignore this expression here, we have three equations. These two are the same. Don't need to ignore it, I guess. And we have three variables. We have a velocity 1, we have a velocity 2, a velocity 3. We don't have anything else. Of course, the head losses would be, in this system, would be delta Z equals delta Z. Same for both. We've already said that they have to equal each other. But not only do they equal each other, we know what they are. They're an elevation. Dam at 5,000 meters, C at 0 meters. And so you know that magnitude. And so we have three equations, three unknowns, and then the tricky part is just solving for them. It's tricky because sometimes they're v squared terms. So you end up with quadratics and cubics like we did last time. So nasty equations. But understanding the basic principle of how we do it, quite simple. Three unknowns are three velocities. We need three equations to close the system. We get two equations by the energy equation through two different circuits, and we get one equation from continuity. So it's exactly the same that we solved Navier-Stokes equations to get the distribution of pressures across a pipe. Just a bit, they're differential equations, but the same idea. You have to have enough knowns in your system, enough equations to solve for your unknowns. Okay? Well, let's not go into the excruciating detail that we did on our type 3 questions last time. I noticed some people busy doing homework in the front last time. So let's not do that again. But let's just go through the gist of it. Actually, it might be. I was tempted to think about doing this. Does it copy it? I think that's not the way it copies. Oh, it does. I will sound so surprised when I actually do something right. Story of my life. Okay. So instead of going through maybe we'll go through the example also, but just state what the question is. Question's pretty straightforward. Flow rate (1 plus 2) is known. I should state the problem. So the idea here is 2 tanks. They're joined by a pipe. This pipe is not there yet. There's a flow between the 2 tanks, which is you don't know, but you know what the head difference is. Calculate the flow rate between the 2 tanks without this pipe, and then calculate the diameter of the pipe you need to add so that you increase the flow by 30%. That's the question. And so how would you solve that problem? Is unknown. Calculate. So calculate circuit 1 plus 2. Then pipe diameter. It's actually quite long if you write it out, isn't it? Then pipe D for, so this gives you Q, pipe diameter for Q2 equals 1.3 times Q. 2 parts of the question. That's the question. So how would you solve it? You want to know the flow through the system. What do you know? You take Bernoulli and you'd write it to these points. You'd get ZA plus PA over gamma plus VA squared over 2G equals no pump equals PB over gamma plus VB squared over 2G plus friction factor pipe 1, L1, D1, V1 squared over 2G plus friction factor length over diameter for 2, V2 squared over 2G. When I rush, my handwriting gets even worse, right? So what do we know? We know this is ZA minus ZB. So we know this, we know this, we know there's no pump, we know it's a big tank, so this actually is 0. We know it's a big tank, so this is 0, and we're taking the pressures on the surface, so we know that these are 0. So we're given a friction factor, so we would know the friction factors for both of these, pretty sure. So we know the friction factor. We're given, we don't know the flow rate, but we want to increase it to 1.3. We know the diameters of the pipe, so we can basically solve that. So we have one expression. We know that these are equal to each other. We know that V1A1 equals V2A2. So these two are linked. So we have delta Z equals some terms F1, L1, D1 times another term, a constant to account for this mismatch, plus F2, L2, D2 times V2 squared over 2G, right? So we know what this is, so we can solve for this, because we know what C is controlled by the ratio of these things, just not doing the substitution. So then we can come back and we can write two circuits. So we know from this will give us V2, and Q is equal to V2 A2. That's it. So long and drawn out, but that's the first part. We've calculated the flow rate through the system. We want to know the flow rate through the rest of it. So now we know that we want Q to equal 1.3 times Q0. So we now need to rewrite this. So we can go through this and we can write two circuits. We can write one circuit, is this. We know that the equation is just going to be delta Z equals, for the top circuit, is going to be head loss 1 plus head loss 2, right? These two pipes. We know that each of these head losses are going to be something like friction factor, which we know L1 over D1 V1 squared over 2G, etc. for each of these. And we're going to write a circuit through here, which is going to be same head loss across the system, equals head loss 1 plus head loss 3. And this one is going to be equal to gel 3 is equal to friction factor length over diameter pipe 3 times V 3 squared over 2G. And so we certainly know what the flow is through here. And so the way we can constrain these equations, I suppose, is that V1 A1 is equal to V2 A2 plus V3 A3. And so really we do have three equations and we have to know what the unknowns would be. So what are the unknowns? We know that V1 A1 equals 1.3 Q0. We knew Q0, so by definition we certainly know what V1 is. And so we've eliminated that. We don't know what V2 is, but if we know what this is and we know we can calculate one of these, then we can solve for the other component. So we know what this is. We know what this is. We certainly know what HL1 is. Equals friction factor length 1 over D1 V1 squared over 2G. We said that we know V1 because we know the flow rate. We know these components, so we definitely know HL1. So we know this also. So we know this also. I guess I should have written these as 2, right, in this mode, because I'm pointing to this one. And then so the remaining portions we need to know are, if we know what this, we know what this is and know what this is. We know everything in this equation because we know that these have to sum up to this, so we can solve for the value of V2. If we know what the value of V2 is, then we know by definition flow rate is in here is the total. We know what the flow rate out is V2 times A2. So we know the amount that we're going to have to reroute down here, which is this amount here. And if we know what this amount is, and we know what the head loss is going to be, because we know how much head loss is eaten up on this first part, we can solve for the parameter that we don't know, which is going to be the diameter. So, I don't know if that was any clearer than going through the numerical example. The numerical example actually lays it out okay. So without going excruciatingly through the example, let's just explore those parts. So we want to know how much water is flowing through the pipe when this one is shut off. So we just have an upstream and downstream. We have a composite pipe of a friction factor upstream, friction factor downstream. So we can write the energy equation as this, and it just comes out to be elevation drop is equal to the friction factor of those two pipes. They happen to be the same diameter, and so they'll be exactly the same friction factor. And so we have one equation here that we can solve for V1. We didn't need to apply continuity, actually, so I didn't notice that. So since the diameters are the same, the velocities in each one are the same, so V squared is the same, and we end up with a velocity. From the velocity, we calculate a flow rate, and we have that. We know that the flow rate we want is 1.3 times that, so we have that. Now that we're putting this circuit in, and we're opening up this pipe, then we can write the equations through here and through here. And we also know that the volumetric flow rate, Q1 has to equal Q2 plus Q3. And so in doing that, we merely do this. So we can enforce that the upstream volumetric flow rate is this. We know what the upstream flow rate is in pipe 1 because it's 1.3 times the original amount. So we have that. We know that if we go through the upper circuit through 1 and 2, we know that this is the expression that's going to judge this. This is this here. And we have many of the components we need, but we don't know what the velocity in the downstream pipe is. We certainly know that the upstream one is, because everything that comes out of the tank, 1.3 times Q has to be the velocity that goes through here. So we definitely know what this velocity is. And so that gives us this expression here with only one unknown, V2. And then we can write our way through the second circuit, which is going through this and coming out here. And this expression is this. Again, the head loss is the same from upstream to downstream. But now we're going through the upstream pipe and the lower pipe we've just added. This is the expression we have. We know the upstream velocity because we have the flow rate. We know the head loss because of this. We know this as well because V3 A3 plus V2 A2 is equal to Q1, right? So we know this. We know, if we know this velocity from here, then we can get this. And so we can define this as a function of V3. So V3 and D are still in this equation. They're related, and we can't get them out. And if we know what the upstream, we end up with this expression where we have both D3 and have solved for the magnitude of V3 as being equal to the volumetric flow rate divided by the area, because we know this. And so I guess physically what we know is if we drew this from upstream to downstream, physically what we're doing is we're getting the head loss, which is really, would be this for the single pipe, but for the double pipe is going to look like this. Head loss in the upper pipe is the same for both circuits, and the head loss in the lower pipe is the same for both 2 and for 3. And all we're doing is enforcing that boundary condition as we come down. I guess notably, the head loss at this point here is not the same for just one circuit as it is for 2 circuits. So I guess that's the crux of this problem. So, but basically, if you take out all the arithmetic gymnastics, we have three unknowns. We're solving with continuity, and we have the known head loss over the entire system has to be equal to the sum of the components on the upper circuit. The head loss on the entire system has to be the sum of the components on the lower circuit. And likely we have velocities 1, 2, and 3, and so we close it with three equations. Actually, we have velocities, we have a diameter here instead of a velocity. So we have two velocities, and we have one diameter, which are unknowns, which we have to solve for. So it's just a little different, but that's the basic idea. So there's that. This is even more complicated, but the same idea. So if you have a circuit where the tanks have two different elevations, then you can't say that the head loss between the tanks is the same for both circuits because they might be different. Also, you have to be aware of the fact that water will flow from the highest reservoir to the lowest reservoir, so you have to figure out which is the intermediate reservoir, because the upper and the intermediate reservoirs are likely going to be flowing into the lower one. Certainly the lower one is not going to be flowing into the intermediate. And so you need to look at what the elevations would be. 838, 850, 805. So the flows in this are going to be in one circuit here, and in one circuit there. And again, you can write the equations, like in the branching one, from upstream to downstream, either along this course or along this course. But now they don't have the same end delta z. So you just have to account for the fact that the elevation difference between upstream and downstream is different between these two. And so if you do that, the same thing. Continuity is, this would be Q1 plus Q2 equals Q3. Right? Q1 is this circuit, Q2 is this circuit, and they have to equal the one going through here. It's okay. And then you write the energy equation for these two circuits. So the energy equation is the difference from A to C is from A to C. So it's the difference in elevations. This was our delta Z before, which is between this tank and this tank. And the flow losses along this pipe and this pipe, which are just written here. And then separately, you can do the blue circuit from B to C. And B to C, well, the difference in elevations of those two. You'd take this to the left-hand side, likely. And it would be the losses along this pipe plus this pipe. And so in big picture, you have, this is delta Z AC equals HL 1 plus 3. And this is delta Z BC equals HL 2 plus HL 3. Same idea. You have three unknown velocities, you have three equations, and you really do have to do some mental gymnastics to get the answer, which I won't bore you with or embarrass myself in doing either way. So that's it. Right on the witching hour, so we won't talk about flow rate measurements. You probably know these things. We've talked about it. Well, maybe we'll spend 2 minutes on Monday talking about that. Leave it there. Okay, great. That's all we'll talk about pipe flow. Really only 2 more weeks of classes. Next week is external flows, flows on wind turbines, on wings, same protocol. We can use the Moody charts, look slightly different, but they're essentially the same. And then open channel flows, how water flows in rivers and ditches. So that'll be 13 weeks. The week before Thanksgiving, no classes, no extra credit quizzes to do, but the midterm. And then the week before finals is also a midterm week. So we're in the final stretch. 2 more weeks of stuff to talk about, 11 and 12 and 13, and then we're done.